Welcome back to our new and free learning platform Catalyst for IIT JEE. This is the third lecture of our lecture series on chemical kinetics, and in this lecture we are going to talk about the integrated rate equations for zero order reactions and first order reactions. However, for better clarity, we divided this part into two lectures. So in this lecture 3, we are going to talk about the integrated rate equations for the zero order reactions only. So before I start discussing the integrated rate equations, I have a very important announcement for students mainly. Students, if you want any lecture notes like these slides, if you want to practice some MCQs, so if you need the MCQ sheets or if you need some books, please let us know by commenting down below in the comment section so that we can provide the materials that you need from our next lecture onwards. Okay. So now what we have learned in our lecture 2, we discussed about reaction coordinate, where this is the reaction coordinate diagram of a very simple reaction where R is the reactant and P is the product. As I said before, that every reactant has to go first a uphill and then a downhill process like this, and the high energy point is called the transition state, and the energy required to reach the transition state from this reactant energy is called the activation energy. We also discussed about the molecularity and order of a reaction, where in this reaction where A plus B is going to form the product P, the rate can be found out from experiment. That rate is equal to K concentration of A into concentration of B, where K is the rate constant. So order of the reaction can be written as sum of the power of the concentration. So power of concentration A plus power of concentration B. So what is the power of concentration A? It is 1, and concentration B, it is also 1. So the order of the reaction is the summation of those powers. So 1 plus 1 equal to 2. Okay. So let us move to our discussion on zero order reaction. So let us consider these reactions where A is your reactant and B is your product. So if we try to write down the rate, so how can we write down the rate? We can write in different ways. Like we can write it in terms of the concentration change of the reactant with time, and also the concentration change of the product with time. But as you already learned about this, that if we try to write down this rate in terms of this reactant, you need to put a negative sign, right? So rate will be your minus dA dt. And also, if this is a zero order reactions, what you have learned in our previous lecture, that the power of the concentration of the reactant should be 0. Correct? Yes. So what will be the rate? The rate will be equal to K, which is the rate constant, into the concentration of the reactant A to the power 0. Now you have two equations, rate equal to minus dA dt and also rate equal to K A to the power 0. Now, okay, now if you try to equate these two equations, and what you will get, then rate equal to minus dA dt equal to K A to the power 0, right? Now anything to the power 0 is 1, so K A to the power 0 eventually becomes K. So what you get finally, you get minus dA dt equal to K. So this is a very important equation which is called the differential rate equation, because this is differentiation, right? So this is the differential rate equation for zero order reaction. Now if I ask you how the rate of a zero order reaction varies with time, okay, now as you can see here, the rate is equal to K, which is a constant, is rate constant, right? Now there is no time term associated with this equation. That means the rate does not depend on time. So if I plot it graphically, this rate versus time t, so what I am going to see, I am going to see a straight line, right? So that means that rate is constant throughout this time. Rate is not changing with time. And what is the value of this rate? The value of this rate is equal to k, as we have seen in this equation. Now let us look at some examples of these zero order reaction. You know Haber process, where from nitrogen and hydrogen you get ammonia, you produce ammonia. But the reverse of this Haber process, where you get nitrogen and hydrogen from ammonia, is an example of zero order reaction. Photochemical reactions between hydrogen and chlorine is also an example of zero order reaction, where you mix hydrogen and chlorine in presence of light. HNO means light, and you get HCl or hydrogen chloride molecules, 2 hydrogen chloride molecules. So this is an example of zero order reaction. Decomposition of N2O on hot platinum surface is also an example of zero order reaction. N2O is getting decomposed into nitrogen and oxygen in presence of hot platinum surface. So this is crucial, that you need to do this reaction in presence of hot platinum surface only. Okay, so platinum surface is a catalyst here, and this specific example is also a zero order reaction. Okay, now let us think these zero order reactions in this way. If we ask this question, that zero order reactions are they elementary reactions or complex reactions? So to answer this, how we need to proceed? What we know from the previous lectures, we know that for elementary reactions, molecularity equal to order, right? Now for zero order reactions, let us consider if these zero order reactions are elementary reactions. Now what will happen then? Then the molecularity should be equal to order, and then the molecularity should be also 0. But can this molecularity be 0? No. Why? Because the molecularity is the number of molecules that participate in the reaction. Now if this number of these molecules is 0 for a reaction, that means there are no molecules at all for doing a reaction. So that means these zero order reactions cannot be an elementary reaction. So for zero order reactions are always complex in nature. Though the calculations, you will see that these calculations for zero order reactions are quite easy, but the mechanism of these zero order reactions are complex in nature. Now let us move to our main topic of discussion, the integrated rate equation. So let us start from the point that where we stopped in our previous slides. This is the reaction. A is your reactant and B is your product, and minus dA dt equal to K. This is the differential rate equation for zero order reaction. Now to get this integrated rate equation, what you need to do? You need to do an integration on both sides. Now after integrating this, you get that integration sign dA, and you put this minus and dt sign dt in this side. So you get minus K dt integration. Now K is a constant, rate constant, and it does not depend on time. So you can put this constant outside this integration sign, and you get minus K integration dt, here dA. Now if you consider this reaction, what was initially at t equal to 0, the concentration you started, the concentration of A was A naught, right? Now after t time, you already lost some concentration or some molecules of A, because you already started getting this product B, and the final at time t, the concentration of A is this one. So this integration here means that at time t equal to 0, you have A concentration A naught, and at time t you have A concentration, this A. Now after doing integration of this dA, you get only A, and after doing integration of this dt, what you get? You get t. So these are the limits, these are called limits. Okay, Now after doing it, what you get A minus A naught, A minus A naught, and you have this minus K, and you get T minus 0. So finally doing the calculations, what you get A minus A naught equal to minus KT, or otherwise A concentration is A naught minus KT. That clearly tells you that when time increases, when you are increasing the time of the reaction, that means this quantity is increasing, and more quantity or more amount you are decreasing from your starting concentration. That means the concentration of A is going to decrease. Now this equation is called the integrated rate equation for zero order reaction. So this is the most important point here in this lecture, where you already know that this is the integrated rate equation for zero order reaction, and this equation will be helpful in calculating all the problems that are going to come in your exam. Okay. Let us look at the graphical representation of integrated rate equation for zero order reaction. Now before we try to see the graphical representation for zero order reaction, so we need to understand how a straight line looks like. So for equation, the straight line having equation y equal to mx plus c, where m is a positive quantity or positive number, what we see this kind of a straight line. Okay, now the slope is equal to m, which can be calculated by this delta y by delta x, and the c is called the y-axis intercept. But when the equation becomes y equal to minus mx plus c, so we have this kind of straight line. Okay, so as you can see here, when you have this minus sign, the slope becomes minus m, and the straight line is pointing downwards. All right. Now here, as we have already seen, that the equation, the integrated rate equation for zero order reaction is A equal to A naught minus KT. So if you try to plot A versus T plot, so what happens, you can compare this equation with this y equal to minus mx plus c equation. Now this y equal to minus mx plus c, as you have already seen, now you put you put A concentration of A in terms of y, you put minus k in terms of minus you minus m. Okay, you put minus k in terms of minus m, you put A naught in terms of the y-intercept c, and x is here the time axis. Now what you get a similar kind of straight line that you have already seen for y equal to minus mx plus c. Now the intercept is A naught, and this equation or this graph tells you that the slope of this straight line is minus k, and with time the concentration of A is decreasing. So initially it was A naught, and with time the concentration is decreasing linearly, and at this point there is no reactant molecule remaining. Correct? Because the concentration of A is 0 at this time. Now with respect to this, we need to know what is the lifetime of a reaction or time of completion. So as the term time of completion suggests, that it is the time the reaction takes to complete the reaction, right? It is the time required to complete the reaction. Now as we have already seen before, that this is the time where there are no reactant molecules remaining. So that means that this is the time where my reaction is completed. Now at this time is called Tc, or the time of completion. Now how do you calculate, or how do we get this Tc value? We need to again use the integrated rate equation for zero order reaction. So we have seen that integrated rate equation is this, and the time at time Tc, what happens? There are no reactant molecules, so the concentration, this A, becomes 0 at Tc. So you get this equation and you solve by putting this Kc here. So KTc becomes A naught, and Tc, or the time of completion, becomes A naught by K. So this is the time required to complete the reaction. So this time is called the lifetime of reaction or the time of completion. Now let us discuss another important concept of these reactions: half-life of a reaction. The half-life is defined as this: the half-life of a species is the time required for the concentration of that substance to fall to the half of its initial value. Now let us understand like this. So initially for this reaction, the concentration of A was A0, right? So what is the half-life of this reaction in terms of this species A? It should be the time required to reach the concentration A0 by 2, okay, because that is the half of its initial value A0, right? Now if you see this graphically, so initially it was A0, the concentration of A, and with time it is decreasing. Now at a point it will reach the point where the concentration of A becomes A0 by 2. See, this whole part, this intercept is A0. Now if you divide equally these two parts, so this becomes A0 by 2. So at this point the concentration of A is A0 by 2. And what is the time here? The time is the T half, or the half-life of a reaction. Now so here how do you get the expression for T half? Again, you need to use the equation of the integrated rate equation for zero order reaction, which is written here. Now at T half, what happens? This A concentration of A becomes A0 by 2 because it is half of the initial value A0. Now if you solve this, you get K T half equal to A0 minus A0 by 2, and finally you get T half equal to A0 by 2K. So before, you already get that Tc, which is the time of completion of reaction for zero order reaction, which is A0 by K. Now you get T half equal to A0 by 2K. Alright. So to solve any problems regarding these zero order reactions, you need to remember these three equations. First one is the integrated rate equations. The second one is the time of completion, and the third one is the half time or half lifetime of the half-life of the zero order reaction. Now let us do some questions for zero order reactions. These are some practice problems. Now the question is, A is going to form product. Now if you started with 1000 moles of A and after 10 seconds you are having 900 moles, right? 900 moles are remaining. Yes. So how much time is needed to complete the reaction? So to complete the reaction, that means the time of completion is needed. That means you need to use this formula, but you need to find out the rate constant first, because there is no mention of the rate constant, right? Okay. So how do you find out the rate constant first? So the values that the initial moles and after 10 seconds the number of moles are given. So you need to use the integrated rate equation. So using integrated rate equation, where A0 is equal to 1000 moles and T equal to 10 seconds and A becomes 900 moles. So you put these values and what you get K equal to 10. Now you have the A0 value, which is 1000, and you have the rate constant value, which is 10. Now you also have the time of completion then, right? So time of completion is A0 by K, and it becomes 1000 by 10, which is equal to 100 seconds. So after 100 seconds, the reaction will be completed, right? So the answer is 100 seconds. Now let us look at some other problem where again the A is giving rise to the product. Now the half-life is given now. If the half-life is 2 minutes, how much time is needed to complete the 75% of the reaction? Okay, so this is important. 75% of the reaction will be completed. So if you use this equation where A equal to A0 minus KT. Now what will be the A? A is the remaining concentration of A, right? So as it says the 75% of the reaction is completed, that means only 25% will be remaining. So 25% of A0 is equal to A. So you can write it like this, 25 by 100 into A0. Now this is given that T half, we know that A0 by 2K, right? So this is equal to 2 minutes because it is given. What you get from here, you get A0 equal to 4K. So as T half equal to A0 by 2K, which is equal to 2 minutes, you get A0 equal to 4K. So you put this A0 value, which is 4K here, right? And you get only K. So you get A equal to K and A0 equal to 4K. So what is required here? How much time? So the time is missing here. So you need to find out the time. So you have A value and A0 value. So how do you find out the time? You need to put it in the integrated rate equation. So A is K, A0 is your 4K. So you put these values and what you get KT equal to 3K. You cancel this K both sides and you get T equal to 3 minutes. Okay, so the answer is 3 minutes. So the 3 minutes are required to complete the 75% of the reaction. But for a MCQ problem, for like competitive exams, do you need to do all these solving problems? No, you need to apply your brain. Now this is the A concentration axis, where this is the reaction completion. Okay, so initially the reaction has not started, that is why it is 0%, and 50% means your 50% reaction is done, and 75% means your 75% reaction is done. So the half-life is given 2 minutes. So that means to complete the 50% of the reactions, you need 2 minutes. So for zero order reaction, this is the best part, that if this half-life, that means that if this requires 2 minutes, the other part also requires 2 minutes, the other half, right? So 50% and here it is 100%. So in between it is 75%. So that means if this is 2 minutes, this is 2 minutes, this portion remains requires only 1 minute. So to complete the whole 75%, how do you get the time? You need to add these 2 times. So 2 minutes plus 1 minute here. So total time required to complete the 75% reaction is 3 minutes. This is only applicable for zero order reactions. Please remember that this trick is only applicable for zero order reaction. Okay. Now in this lecture, what we discussed about zero order reactions. We discussed about the complex reactions. Zero order reactions are complex reactions. We also talked about some examples of zero order reactions. We identified the differential rate equations, and we also solved the integrated rate equation. Now graphical representation also were present in our lecture, and we also solved some problems on zero order kinetics. So if you like this video, please like and share with your friends, and do not forget to subscribe and hit this bell icon so that you do not miss any video from our channel. You will get notified when we upload our next video. Our next lectures are coming soon on organic chemistry and as well as on electrochemistry. So stay tuned with us. Thank you very much for your attention.